Hi, I am Roberto Vasquez, a member of the Institute of Astronomy of UNAM located in Ensenada. At this moment, we are going to continue with the workshop focusing on high dispersion astronomical spectroscopy. Since this is the second session, we will begin by covering the fundamental processing of the images. We will have a discussion about the preliminary procedures and bias subtraction, followed by the calibration of the wavelength. Prior to motivating individuals to participate in exercises, it is crucial to perform basic processing as a preliminary step and subtract any biases that may be present. Keep in mind that following observation, we will possess specific images that are accessible. As an illustration, we will possess the bias calibration images, which, as I previously mentioned, are associated with a pre-charge that has been applied to the detector, as I have explained before in detail. We will also have images referred to as image slit, where we will have the image and the slit superimposed together in order to precisely determine the location of our slit as it passes through, thereby enabling us to obtain our two-dimensional spectrum accurately and effectively. We also have the spectra of the object, which we typically acquire 1 or acquire 3. If you want to obtain cosmic ray subtraction using the median method, you need to take 3 exactly identical spectra, not just one, and have a comparison arc for each of the filters we use. In the event that we direct our attention to one of the spectral lines, we will make use of a specific filter, and as a result, we would be in need of an image of the comparison lamp, the comparison arc, thorium and argon for each of these filters. With regards to the preliminaries, it is important to note that during the manufacturing of the detector itself, there may be instances of poor performance of the pixels at the edges. As a precautionary measure to prevent any unexpected issues during data processing, it is customary to trim a few pixels, usually up to 5, for example. This helps to ensure optimal performance and minimize any potential disruptions that may arise from the edge pixels. Another factor that also serves as motivation for us to trim a bit is when our slit is completely covered by the detector, leaving no room for any light to pass through, and there is still extra space left on the detector that could potentially be utilized. Therefore, in that particular case, it is not advisable to utilize the complete size of the detector, but rather to crop the image precisely at the point where the arc lines begin to disappear. So, in order to do that, you need to display a comparison arc, observe it at the ends, towards the beginning or the end of what would be the slit. And in this particular case, we can take this area as an example, where it is evident that the slit is gradually starting to disappear and become less visible. I would take something resembling this, that diminutive square, and then we would need to determine which pixels to crop from our image. If we are going to crop it in the x-axis, we need to give the incopy command to the initial and final ends of the x-axis in order to achieve the desired result. If we won't crop in x direction as no bad pixels, we simply place an asterisk, then 2 dots, and indicate other sector, which would be other interval, that is y interval, initial y, and final y. There, for example, if we don't have anything to trim in the initial y, then a y is placed and the final y goes as far as the yellow line of this reaches. This is a portion of what I typically do with my images, and in this particular manner, I do not have any results or findings there at that location. Short press is also an interesting point to note for the preliminaries. In many cases, we are going to utilize groups and apply various operations to groups of images, which adds a significant level of efficiency and flexibility to our approach. This group-based approach is a crucial aspect of our methodology. For instance, there are times when our files are named B-fits, all the Mezcal2b images, Mezcal2b, and then somehow group all those that have or end their name with B-fizz. For example, when performing bias subtraction, we take multiple images, as discussed in previous classes, and create a super bias using the files command, which simply names the files with B-fits in their names. This process involves taking several images combining them to create a super bias, and using the files command to specify the files with bfits in their names. This is an essential step in bias subtraction, ensuring accurate calibration of the data. We then create a file that is just the list of biases. We can also create another one utilizing the objects. There, I have included an example with fix. However, if we are unable to group them by name, we can list them one after the other using a comma. Object 1, Object 2, Object 3. And it is important to always use this greater than command to position it in another list, ensuring proper organization and clarity of information. Once we have the necessary information, we can proceed to make all the cuts using a single command. This command would involve copying the diagonal twice and adding the mentioned interval. Finally, we place the resulting image at the list of roots using the diagonal twice and the letter T. This process allows for efficient and streamlined execution of the desired actions. What does that mean? It means that a T will be appended at the end of the name of every object. It is a command that I learned when I was already quite grown up at the time of learning it, but it has been very useful to me in many ways. So it can be accomplished using a list, or it can be done individually. I simply wanted to mention the existence of these tools, but once the images have been cropped, we can proceed. Perhaps we would need to create new lists with the updated names, etc. For instance, consider a scenario where the images are already cropped every day, and if there are only a few, we could view them individually. Here is an image of a track for you to see what it is. If you move your mouse over the image, you will notice that there is a certain level, a level that could be 1000, could be 500, could be some number that you will see as a fairly uniform average. But of course there are fluctuations from pixel to pixel, and that is what it's all about, averaging many biases and considering the variations at each individual pixel. So one of the things we could do is to carry out statistical analysis on the biases, the limiting factor, which would in some way help us in understanding what the statistics are showing and gaining insights from the data. For instance, in this case, one is able to observe the average value, the standard deviation, the minimum and maximum values, and occasionally there exist outliers such as the final one there, which are markedly distinct and may potentially be attributed to a cosmic ray colliding at the precise instant the measurement was being recorded. Well then, in order to create the average bias or the super bias, you have to utilize the zero combine command. So you will need to delve into the task families, right? Is that the correct understanding? One component that is essential is CCDRF, and within that, the EPR must be set to 0 in order to combine effectively. When one performs the EPR, it is done in order to edit the parameters that a specific task may possess. In this zero combine, simply we just have to be extremely cautious that the input is exactly and precisely the list of roads without any errors or discrepancies. Here we would have the list of roads and then a common name, if you want to name it vias, super vias. I put super vias there. You can name it 0. The default is to name it 0, the name you prefer, because it will be a single combined file of all the days observed for that night. Another factor to take into consideration is the type of combination, which would be an average and potentially utilizing the cosmic ray rejection mode, the CR reject, to instruct it that if it detects something with a very high value, then it should not include it in the calculation process. Another very important thing that is present, indicated at this location with an arrow, is that by default, the command typically specifies that the 200th image type is 0, which signifies that they are bias. However, certain telescopes like our 2MED telescope do not include that command in the header, so we do not have any way of simply knowing from the headers that it is an image via. This lack of information in the headers poses a challenge for us to identify the nature of the data captured by those telescopes. So we simply eliminate there if the default command indicates 0, We merely remove a space, one arrow, and with that, whatever is present disappears. And with that, remember the method to execute any command in the air emanating from the EPAR is :go or simply :G, and this will accurately execute the combination command of zeros, ensuring precise execution of the desired action. Once the zero combine command is executed, the file that combines all the biases into a single file, which would be referred to as the super bias, is generated, specifically the zero, as you may have desired to name it. To confirm the importance, rerun the instat command, the one mentioned, and then run im statista vias, again. This time, the super bias file is included, and the previously seen statistics are listed again. It can be observed that the super bias file has the same average value, but the standard deviation is significantly lower than any of the previous files, indicating its significance. This confirms that the previous results were not due to chance, as the addition of the super bias file has resulted in a more precise and reliable outcome with a reduced standard deviation. You can also observe the minimum and maximum values, and they are indeed much closer in proximity to the average, which makes this file statistically much more superior and reliable in terms of data analysis and interpretation. And now we have the opportunity to proceed with the process of subtracting the super bias, which involves removing that pedestal from all of our important images, specifically the images of the object and the comparison arcs. So here, for example, I executed this command imarit, which is short for image arithmetic. I provide it with the input objects minus the super bias, and the outcome will be objects diagonal B, which indicates that it will append the letter B to the end of each file name. Therefore, it will iterate through each file, performing pixel by pixel subtraction of the super bias, using the bias value as a reference. Upon executing the program, as can be observed, a plethora of files named bfits were generated, which already incorporated the subtraction of the super bias file to some degree, thereby indicating the successful completion of the process. Well, now let's have a brief discussion about cosmic rays. Cosmic rays, which are charged particles, often ions, originate from various parts of the cosmos. They can come from different locations within the galaxy and are closely associated with supernovas. There are processes that generate these particles, enabling them to travel throughout the galaxy. In fact, some of these particles are involved in causing intriguing phenomena in living beings that are related to the process of evolution. Are cosmic rays of scientific interest? Yes, there are scientific disciplines that study both the generation, transport, and the effects of cosmic rays on different systems. However, for us, observational astronomers who use detectors like these, based on the photoelectric effect, essentially when a photon falls, certain electric charges are released. The issue arises when we receive electric charges that do not correspond to our target. And cosmic rays are some of those varieties of charges that we do not want to take into consideration or include in our analysis. While conducting the observation, we receive cosmic rays, which subsequently persist in our image when we read it, necessitating the need for their removal. That is fundamentally the topic at hand. Here, as an illustration, is a spectrum that we are going to focus our efforts on and work towards improving. It is a spectrum taken with the hydrogen alpha filters plus nitrogen. It looks very good. The most luminous region corresponds to the H-alpha line. The two areas that are slightly less bright at the extremities are attributed to nitrogen. There is an additional faint line present, located adjacent to the nitrogen line, as well as a small spot in close proximity to the nitrogen line. These features are known reflections, similar to the small halo surrounding the H-alpha line. It should be noted that these reflections are an integral part of the image and cannot be eliminated through image processing techniques. However, for instance, they have the ability to observe other fascinating phenomena. The intense line that cuts through the hazy regions represents the central star of our planetary nebula. Stars, as we had mentioned at a certain juncture, seem to be horizontal from our perspective. Then there are more stars below, more stars above, seen fainter. We also have the vertical lines, and as you'll recall, the vertical lines correspond to the emission from the sky. All right? Well, in that case, obviously, what infiltrates this unfortunate range is an astonishing quantity of bright small dots, which are the cosmic rays that fill the spectrum. Those are the ones that require removal, okay? Well, there are numerous methods available for this task. My favorite method is the median method, where three identical spectra are taken and combined using a command similar to the zero combine. But this is the catch. Basically, they use the same routines, but they have different goals. So, what the inCombine command does is combine three exactly identical spectra and takes the median value, meaning it removes the highest, removes the lowest, and keeps the one in the middle. An interesting method, as if the three things are identical, it won't matter, since the fluctuation is too tiny to affect the value. But when a cosmic ray falls on one of them, on a pixel, that value is going to be much larger than the other two. So utilizing the median value instead of one of the extremes is indeed a fantastic method to effectively remove cosmic rays from the data. What's the problem? We'd need to observe the same spectrum 3 times. If we want to observe it for 20 minutes, it would have to be 3 observations of 20 minutes. We triple the duration of exposure for every object. There are additional tasks that it performs, but on the whole, it is highly satisfactory. ERAF has additional tasks such as cosmic ray or emedit, which also aid us in removing cosmic rays in a way that can be more intricate, time-consuming, and demanding to achieve an efficient, quick result that is both effective and reliable. In the years that followed, an external program named Cosmic came into existence, and I strongly urge you to look it up on the internet because it has proven to be remarkably effective, incredibly effective in its ability to mitigate the impact of cosmic rays. Okay? So, from the ones I have worked on, it has turned out to be quite successful in every aspect. So I suggest that you search for it on the internet. The address where you can get it is available. The article is accessible for reference to the method. It is Laplacian identification of cosmic rays, and the authors of the work are listed there. A truly very good program. So you have to download the software and then proceed with the installation process on the computer. Actually, they have multiple versions for IDL, Python, C, and ERAF programming languages. If you're learning or in the process of learning how to reduce data with Python, it'd be interesting for you to use these routines because they've been extremely helpful to me. So I discovered that the version of the file we should utilize is the image version, since for a program of this nature that operates specifically by purifying images, it is unable to differentiate whether we are observing an object, a spectrum, or an image, because what it perceives is the emission and cosmic rays. Then it dawned on me that the precise image version is the one that, in the case of Mezcal, will be of great assistance to us in effectively removing the cosmic rays from the equation. The downloaded file at the end is named LACOS in CLA. Then, our login 150th file must be modified using the task LACOS command wherever the Cosima file is located. By doing this, we can activate it and make it functional for its intended purpose, ensuring that the necessary changes are implemented and the file is ready for use. Another crucial aspect that cannot be overlooked is that this program, this task, requires the utilization of routines from the Space Telescope Science Institute, which have been an integral and long-standing part of ERAF for a considerable period of time. After a certain period of time, to be precise, in version 2.17 of ERAF, the STS DAS is not found, but fortunately, the latest version of Noir Lab, namely version 2.18, which happens to be the most recent version of ERAF, does have the STS DAS routines. You just need to run the command, simply type SET, and that will activate those routines for you, ensuring smooth execution of your tasks. Once the routines are activated, we are now able to make use of them for loops and then proceed to set them in motion. In order to make the cosimpulse work, All you need to do is give it a name, an initial name, a final name, and specify a name for a file of bad pixels map. After that, you have the option to tweak the parameters according to your preferences. However, if the default parameters work well for you, there is no need to make any adjustments. Simply leave them as they are and proceed with using the Cosimpos tool effortlessly. Within the manual, in the program article, there exist detailed explanations precisely outlining the purpose and usage of each of those parameters. Well, and voila, here you have, for instance, prior to the cosmic and subsequent to the cosmic, and indeed it can be observed that an effort was made to eliminate cosmic rays. There are a few small spots that apparently did not come off, which could now be removed with the emedit, but they are a couple of peaks in the right area. However, it has truly been an extremely commendable task in which the objective is specifically to maintain the original emission of spectral lines intact, while solely eliminating the interference caused by cosmic rays. Well, thus far, we have successfully addressed the preliminary part and thoroughly examined the various routes that are available for consideration and exploration. Following this, we will proceed to examine what wavelength calibration entails. However, at this moment, we can affirm that we are fully prepared to initiate the process of calibrating our various aspects in terms of wavelength. So we will proceed with the remaining content in the upcoming class. Thank you for your attention.